All right, welcome to the next lab in CTC 115, Quality Control Laboratory. That's the class you're in. At least I hope you know that's the class that you're in. But this is yet again, I'm so sorry, but this is yet again another review lab. At least part of it is. Well, the second half of it, no one's seen, so we get to start from a blank slate with that lab experiment. So that'll be great. But CTC 114 people, if you have taken CTC 114, you have seen the beginning part of this laboratory exercise already, and this is the basic use of the pipette, and that's what we're going to be learning about in this lab activity. And with this little short, oh, you know me, it's going to not be short, but this little short pre-lab lecture is going to talk about the burette, at least give you some idea of what you're going to be doing in the lab when you show up that day, and then we can pick up and run from that point on, and hopefully you won't be running out of the lab, because hopefully it's not that bad. Okay, well, anyway, the use of a burette is a pretty standard piece of volumetric glassware. And the reason that we use this burette is most of the time for titrations. And that's something also that we're going to be doing in this lab exercise in the second half. And now you're thinking, well, I was in 114 and I was doing a month and a half of titrations and you're going to say part B is new? Well, yeah, it's new. You've not done that particular type of titration before. So it's going to feel familiar, but you've not done that kind of actual lab exercise before. Anyway, a use of your burette, this volumetric glassware, is very similar to something like a volumetric pipette or a micro pipette in the fact that it is built to deliver, and it's going to deliver a certain volume for us that we can keep track of as we do a laboratory experiment or as we're following an SOP in a lab environment. What this means, I want you to go back and I want you to think about the pipettes that we've used before. And the pipettes had an etch mark, right? So this etched mark is the line that we need to pull our volume up to. So the meniscus, the bottom of that meniscus is sitting on the etched line of that glassware. But as long as we do that, we deliver one volume, meaning that if this was 5 milliliters, that volumetric pipette is meant to deliver 5 milliliters. And it does that with very high accuracy, and you should be able to do that with very high precision. I mean, this is something that is going to not be a problem most of the time in routine laboratory work, as long as I know how to use the tool. Oh God, I'm getting so excited. I'm getting choked up just thinking about it. All right, so that was the story with the volumetric pipettes, but the issue here is that, well, they are meant for one volume. That is kind of why we did them. So there's going to be moments in time in a lab as I'm working that I need something that can deliver multiple types of volumes, not just one volume at a time, but I need to be able to control it because it's going to stop and it's going to start at different moments, and sometimes it will take more volume than others. So I need something that's a little bit more clever in design than a volumetric pipette might be. Okay, well, now you're thinking micropipetters. Yeah, micropipetters, can be dialed up and they can dial down. So they are meant to deliver different types of volumes for me, but micropipetters are really going to stop traditionally at 1,000 microliters, which is 1 milliliter. And yeah, we've got automated pipetters, and we can go higher than 1 milliliter. They're not necessarily termed micro anymore, but we can at least go above 1 mil in a lab environment. Well, that's really not the same either, because that is kind of the idea that I can dial it up to a certain volume and it will deliver that volume. So in a roundabout way, I'm still using this one volume problem scenario. So if I'm using a glass volumetric pipette, I get one volume choice and that is it. If I'm using a micro pipette, I have to dial it to one volume, and that is it. That is what I deliver, and that's how I'm supposed to use the tool. So micropipettes are not going to do the trick either for this particular type of scenario that I'm getting ready to work with. Okay, now you're talking like graduated. Well, there's graduated volumetric pipettes. Yeah, there's graduated pieces. They're not the best. I mean, you know, all the time we want to go to that one volume stamp whenever possible, because the graduated volumetric pipettes, they are going to have a little bit less accuracy and a little bit less precision than the normal standard run-of-the-mill volumetrics do, but they still do an excellent job. But yet again, I have to make a determination on what to pull up and what to deliver. And that is not the scenario with the Burette. This is me going in to do a lab test, and I don't quite know what volume it's going to take in order for me to do that experiment or that activity or that SOP the best way possible. So a Burette comes in to fill in the void. So this is what a Burette looks like. I mean, that's what you're seeing here on the picture to the left-hand side. And a Burette is volume based. It is for me to fill it with volume of some sort. And this could be water, and it will be water in the first part of this lab exercise. So I'm going to fill it full of water, and then what's going to happen is that there's a valve on the bottom of this Burette. So here is the valve, and that valve is more properly called the stopcock. And that stopcock is going to be able to turn, and you're going to be able to turn it on, and you're going to be able to turn it off. That will stop and start the flow of liquid that's inside of the volumetric pipette. All right, so we'll talk more about the stopcock here in just a second, but that's overall the idea that a Burette is going to bring to the table. So I can fill this full of solution, whatever that might be, and then I can open up the valve or the stopcock area of the Burette, and then what will happen is that I will get a drip, 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 drip out of the end of the Burette. And then when I think that I have had enough volume, because visually maybe something is changing and something is happening and I can catch it, then I can stop the stopcock so I can turn the valve off. And when I turn the valve off, I'm going to have an initial volume of solution in the Burette, and then as it drip, 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 it's going to drain down the Burette, and we are going to kind of be able to measure a volume that we've delivered. And this is how it changes from a volumetric pipette or a micro pipette and those types of things, because there's graduated markings all up and down this really long piece of glassware. And those markings are on there to tell you what specific volume you are standing at that moment in time. So it gives me a little bit of flexibility. It allows me to deliver various volumes to a sample or to a solution for whatever reason. We'll learn about it in part B. And then it allows me to stop it, and it allows me to record somewhat the exact volume that we are using in a laboratory procedure. All right, as with volumetric pipettes, these burettes do come in Class A and Class B. As before, we order everything with Class A's so we could minimize our errors and we can get some better precision with this type of material. And that's really kind of what we keep in our laboratory. You could actually be using Class B's in a lab. Maybe they don't want that precision and accuracy. Maybe they don't have to do that, and they can save some money. And they can save some money by ordering Class B's, which are going to be way cheaper. But we've always had really luck with Class A's. They've done exceptionally well, and we got luck because I can sniff out a clearance deal. If it was from here to Raleigh, I'd be able to sniff it. So we always luck up, and we order a little bit of mass quantities when we can for our Class A burettes and any other thing that we need for our lab. So good job to me. All right, so here in the middle, it's just going to zoom in on the stopcock area, which is that valve that will open up and turn. And I want you to take a look, if you can, this area right in here with the stopcock, and I want you to see how that is assembled. So whenever we clean these and whenever we dry them, we normally take out the stopcocks and we clean those and we give those a good dousing as well. And we leave these to the side, probably on like a drying mat or a paper towel or something, because these are plastic and those plastic things cannot go into the oven. No, 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 I'm going to melt the plastic all over the place. So because they can't go into the oven, then I have to hand wash them and I have to dry them. Just let them naturally air dry. That's going to be okay. But That means that when I go to a burette, I'm going to be able to get a burette, but there's a chance that a stopcock might not actually be there for me ready to go. So I'm going to have to find one that fits, and I'm going to have to make sure that I'm going to assemble it in the proper way. So if you find a stopcock, not one size fits all, okay? No, there's no fits all here. So you're going to shove the stopcock, this kind of white piece, PTFE material, you're going to shove that into the burette, and then what you're hoping is that there's a hole that's going to be here, and that hole is going to line up where the exit points are going to be in the burette. If that hole does not line up there in the center or close to the center, then you've got a wrong stopcock that is meant to go into a different piece of volumetric glassware, or a piece of glassware, period, that we use in a lab environment. So you're always going to double check that first, and if it does line up, then great, you can use it. And then over here on the left hand side, what happens is that if you see this red kind of plastic looking piece, that is what's going to go on first. So I'm just going to kind of say plastic piece is going to be number 1, and then number 2 is going to be kind of that black rubbery type of material right there. So number 2 that you're going to slide on top of that will be your O-ring. And then number 3 is going to be the threaded piece that's going to be out here at the end. So that is the proper way to assemble a stopcock. That plastic kind of washer, if you want to think of it as that way, it kind of just makes sure that that stopcock is held in place, and it provides a flat surface against that stopcock area that will hopefully seal the deal. So we don't want any leaks out of the stopcock, only leaks out of the tip. That is where I want my drops to come from. And that plastic washer is going to just butt up against it, and it's going to help just the solution to stay there. It should not be leaking, but that plastic washer is just an extra little oomph that we can use to make sure it does not leak. The rubber O-ring is going to allow some pressure to be placed onto that plastic washer, but if you put too much pressure on it, it's going to snap, it's going to crack, and it's going to damage and ruin that stopcock connector. So that O-ring is there as just a little cushiony device to make sure we don't over tighten. And then of course the threaded piece is there because that is the way we do tighten and secure things on the stopcock. So the more that you turn that threaded piece, the tighter the stopcock is going to get, and we need it to be able to turn. So we don't want to over tighten this area, because if we over tighten it, we won't be able to turn the stopcock, and that is the whole reason of using a burette in the first place. Here was an original picture of a burette. Woo! Gosh, I mean, I think I probably grew up in this day. Either way, this is often just like a little piece of plastic that was there at the bottom, some type of rubber tubing. You saw a clamp on it, and that clamp, of course, just clamped down against that tubing, and it prevented flow out of the burette. So if I wanted to do some titrations, that was great, because I would go over to that clamp and I would just take my finger and thumb, and I would just give that clamp a light squeeze. And if I did that, and if I did it in a controlled way, then guess what? I would get my drip, 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 drip out of the bottom, and I'm ready to go. I'm ready to titrate. Give me 100 samples. I'll sit here and squeeze the clamp all day if that's what you want me to do. Well, okay, that's kind of what was going on back in the day. So these are manual burettes, and they are going to require you to operate the stopcock. But I also want you to understand that we do have different types of burettes in today's laboratory, though, and these are going to be more automated types of instrumentation that's going to be able to titrate for us. And it kind of takes the place of a burette. The problem, though, is that it takes training to learn how to use the machine the right way. It also requires cleaning, so we want to make sure that we keep these instrumentation pieces all nice, clean, sparkly, and shiny, just like they were when they showed up in the box. So there's going to be a little bit more involved on the equipment end of things. But if I am titrating like 100 samples, maybe I don't want to do this by hand, and the automated instrument can actually do that for us, and it can change the samples as well. So if I've got a carousel, and that carousel's got like 30 samples loaded up into it, I just tell the machine what I want and what I need to titrate, and it will take over and it will begin titrating all of those samples for me, one after one after one after one after one. And that's great news, because that frees me up to go do other things like watch Netflix, and I still get paid. What? Oh, what kind of lab are you working for? It's my secret, I'm not telling. All right, so a little bit of terminology here. A burette, now you know kind of what that means and what we're going to use them for. In our lab environment, environment, we will often order 50 milliliter burettes. That is the typical size that we utilize for the most part in our lab activities. And we customize these lab activities to make sure that 50 milliliters actually makes sense. So for instance, if I'm doing a test and it's only going to require 0.5 milliliters, then I probably don't need to use a 50 milliliter burette in order to deliver 0.5 mils of solution. No world does that make sense. So we do have them smaller, and we go as small as 10 milliliters at least. But when I say this, what I'm talking about is that we have picked out some of these operations that we're going to be doing with burettes, and those operations tend to be at least 10 milliliters or more. Not every single time, but 10 milliliters or more of titrant that's going to be required, which is the solution in the burette. And because of that, we feel really good about using our 50 milliliter burettes to hold that amount of sample. We often process samples more than once. We've talked about that before in other lab experiments, and this is no exception. So of course, we're going to need more than 10 milliliters. And if we do them in triplicates, then 10 mil, 10 mil, 10 mil, that's 30 mils. 50 milliliter burette, if you fill it to the top, well, you got a little bit of extra that's left over, and that extra is there just in case you want to do a fourth or a fifth trial because you've messed up one of the titrations, and you know that you've messed up one of the titrations. So you just want to go ahead and maybe do a fourth or a fifth and add that to your data set. Either way, 50 milliliters are going to be our traditional volumes for our burettes, and we do have the capabilities of going down to 10 milliliter burettes. We just don't have a lot of them, but they're in our lab. General cost of a burette, depending on where we order them from and if I can sniff out a deal or not, will range anywhere between $65 to $250 each, and that is for Class A. So by no means are these things cheap. Handle them with care. Make sure that you pay special attention to the alert, 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 alert. Make sure you pay special attention to the tips of the burettes, because if you don't, that piece can be damaged quite easily. You can knock it up against a container. You can knock it up against the sink basin. I mean, you can accidentally drop them. That is going to be the area that we're most concerned with, because when that tip gets slightly damaged in any form or any fashion, the entire burette now is out of commission. We have to throw it away, and you've just ruined maybe a $250 piece of glassware because of klutziness. So things are going to happen. I don't want you to kind of get worried with it, but things are going to happen in the lab, and you're going to be a little klutzy sometimes. I'm klutzy sometimes, and I'll break things sometimes, and you'll break things sometimes, and it could be necessarily a burette. Absolutely, it can be. So don't freak out or worry about it, but at the same time, please pay special attention, because somebody's going to have to fork out the bill, and that somebody is going to be me. So just handle them with care, please. The stopcock, we talked about the stopcock now. Stopcocks are PTFE material for the most part. They do have glass versions of stopcocks. And the glass versions are out there, and we learn about this in CTC 114, but the glass versions, those need like extra grease and some lubricants, and there's a special way that we've got to clean them. We just don't like using glass stoppered or stopcocks on these burettes. So for us, it is typically this non-stick type of material that is very chemical resistant, and that's going to be PTFE, or aka Teflon, if you want to think of it that way. Titrations. The titration is just the process of using a burette in order to determine a concentration of material. So I've got this sample that's been submitted to the lab. I need to figure out what is in that, like how much of it, I guess. So how concentrated is it? Is it super strong? Is it very weak? I mean, what's going on? So a titration is used, and that's the process that we refer to when we have these samples that come in, and I load a solution up into the burette, and I open the stopcock up, and there's a reaction between the solution in the burette and then the sample that I'm trying to measure. And that reaction is very often going to give me a visual indicator of when it's done. So that process is called the titration. I am titrating the samples, which means I'm trying to find the concentration of of them, and I'm doing that using a burette with a some type of titrant is what we call that in the burette. So the titrant is the next kind of word or definition that kind of gets focused here in the lab directions, and a titrant is the solution that goes into the burette for me, so that way I can begin the process of titration. So for instance, I mean, these can be acids such as HCl or H2SO4. These also could be bases, and those bases could be KOH or NaOH. Very often they are acid-base driven. They don't have to be acid-base driven, but very often, especially in the beginnings of the world of titration and learning about them, it is going to be acid and base focused. But folks, there's so many different types of titrations that are out there that acid and base are just one of many options that we can use a burette for. Standard deviations coming back. Oh God, no more math, more stats. Yeah, that's right. Standard deviation is coming back for us. So here's the standard deviation equation. And I was like, hey, we're not going to do this equation because who does that in real life? Nobody but a math teacher that wants to make your life miserable. So what we'll do is that we'll go into Excel and we'll hit equal and we'll do STDEV and we'll open the parentheses up. Please do not use any other modification of STDEV. We like to be consistent with all of our labs, and we just use the basic standard STDEV calculation. There are options in Excel for you to choose from, but do not choose those options. They are meant for other things, and sometimes they might apply to what we do, but we're just going to keep it consistent. That way we don't confuse you throughout your time while you're in the program. So STDEV, open the parentheses up, highlight the data, and allow it to calculate how close that your values are to each other. A couple of different types of titrations. I just mentioned this idea or concept of acid and base, and that is one of the versions, but we've got so many other reasons to use titrations and to use burettes and even automated titrators, of course, and I've listed just a couple of them here. So up here at the very top, it's a biodiesel titration, and you actually do this in the summer course that is going to be required of a program. So in the summer, you know, the scheduling is very free-flowing, and we know that you've got things to do in the summer, and we know that you've got vacations planned and you go off with your families. So we want you to be here, we want you to do labs, and we want you to do labs in person, and we kind of let you make your own schedule in a way. Just as long as you get the labs completed, that's really all that we're going to be asking for. And one of these labs is a biodiesel production lab. So how can I take spent vegetable oil, and how can I take that used oil and then convert it into diesel that can run a vehicle? That is biodiesel, and we're going to go through the production of that and talk about that a little bit in that particular course. Well, one of the titrations that we can do, there's many titrations that we can do with the biodiesel, but one of them can happen in the very beginning, and that is to see how much acid is inside of that used oil, because we want to neutralize that out, and we want to make sure that we don't have very acidic used oil to start with, because that's going to interfere with some of our catalysts and some of our reagents that we need later on down the road in order for that biodiesel production to happen the proper way. So biodiesel titration, you will see at a certain point. The next is a Kjeldahl method, and Kjeldahl is really focused on the amount of nitrogen in a sample. So this is not the only piece. That's not what Kjeldahl is. Kjeldahl is more full body. There's more steps that are going to come along for the ride, but part of this is a titration at the very end, and that titration is going to be used for nitrogen content. So for instance, I can bring in a soil sample, and when I bring the soil sample in, I can process this a certain way, and I can Kjeldahl it, and I can free up the nitrogen content in that soil, and then I can capture that nitrogen content, and then at the very end of the Kjeldahl method, I can then titrate that sample in order to determine how much nitrogen is actually going to be present. Another way that we can use Kjeldahl is in the food chemistry aspect. So this is actually going to happen in our CTC 235 course. You're going to see Kjeldahl show up, and that Kjeldahl experiment is actually going to be focused on a food product, and then we're going to process that food product, aka milk, And we're going to free up all of the nitrogen that is going to be in that milk sample that we have brought into the lab. And then when we do that, we can isolate that nitrogen and we can titrate that nitrogen at the very end, and that's part of the Kjeldahl method. So you're going to do a Kjeldahl in the summer course, which is CTC 145, and this is CTC 145. But Kjeldahl is also going to come back in 235 in our food chemistry class. So why are we so concerned with nitrogen in food chemistry? Well, that's because nitrogen is specifically tied to proteins, and proteins are going to be on the nutritional label of any of these food products that we are eating or that we're consuming. So whether they're solids or whether they're liquids, those protein amounts, carbohydrate amounts, fat amounts, all of those are going to be listed there for a consumer, and this is one of the ways that we can kind of determine how much protein is in that sample. Saponification value is next. Saponification value says it measures the amount of fat in a sample. So that is what saponification value is going to focus on. And believe it or not, we're actually going to do this in this particular class. So later on down in the semester, we're going to see a saponification titration, and it's going to be just a different way that we can tackle some of these samples. A titration is going to be required, and a titration that's going to be required is going to be looking for AKA fat, and we'll talk more about that when that lab kind of hits later on down the road. Winkler titration is next. Winkler titration used to determine oxygen content in water. So oxygen content very often going to be called dissolved oxygen. So of course we want water sources to be very healthy, and that does require oxygen to be present. We don't want stagnant, nasty, filthy, dirty water. So the Winkler test is going to help us to determine dissolved oxygen or oxygen content that's in that water sample. We have probeware that does that now. It's very similar to a pH meter. We dunk the probe down into a water sample. We can record those values that show up on that meter, but a titration is also one of these options too. Sometimes we introduce this in CTC 114, and that is our wet laboratory course. There's a little bit of more environmental that normally happens on the back end of that class, but depending on the cohort, depending on the year, depending on our weather schedule, how many classes have been canceled due to hurricanes and that type of stuff, we might didn't get to that part. But if we did not get to that part, you didn't miss out on anything. It's still just a straight up titration, just the sample processing is going to be a little bit different. Vitamin C is another titration that we can talk about. This also is going to be in our CTC 235 course, which is food chemistry, and it provides vitamin C or ascorbic acid content in a sample. So sometimes we can get these food products or these fruit juices, and they will tell us how much vitamin C is there on the nutrition label, or somewhere on the label at least. It will say like 100% RDA, recommended daily allowance. Okay, well, we're going to hold them true to that. So is there really 100% of vitamin C in that sample, yes or no? So there's a way that we can determine that, and one of the ways, there's many ways, but one of the ways is through a vitamin C titration, and we use an indicator called endophenol, and we titrate, and we get these color changes, and we report them, and a burette is used for that as well. So burettes are used for all of these so far. Next one's Benedict's, and a Benedict's is just quantifying glucose. That's all that is. Sometimes clinical chemistry can utilize titrations as well. Very often, though, they have very simple little tricks that they can do to simplify their processes to limit the mistakes. But if we wanted to titrate the amount of glucose in someone's urine in our lab, we can do that, and we can do that simply using a burette and a titrant and some type of color change that would begin to happen. And then finally here is listed as Carl Fisher. This is KFT. That is the abbreviation that we use for that. And Carl Fisher titration analyzes the trace amounts of specific water. So not moisture, but water. Moisture is something different. It's defined as something different. But water, H2O, like legit H2O, how much is actually there. So a Carl Fisher titrator will allow us to do that. Again, sometimes these are going to be in CTC 114, and if we did not get to that point, we're okay with that, because we know that that Carl Fisher titrator is going to be coming back in CTC 115 for sure. So if we miss out the first time, we've got a 115 that comes back and picks up some of the loose pieces, and a Carl Fisher titrator is one of those that we always make sure that we hit, at least in one of these two classes for sure. All right, so all of these are examples, absolutely. And more importantly, most of these examples you're going to be doing yourself in a working laboratory. And that's our lab. Oh, we're so excited. All right, so in a class problem, suppose a technician is verifying the accuracy of a burette. A technician delivers 26.52 mils of water, and they do that 6 times. And he weighs each sample. So the density of water is close to 1. No, it's not exactly 1. It's close to 1, but not exactly 1. But we're going to kind of just say, okay, yeah, whatever. So 26.52 mils should weigh 20. That should be 26.52 grams. But I have corrected it here because if we were doing 1 mil per 1 gram per mil, then it would be 26.52 mils. But it's a little bit lower, and that little bit lower stuff, we're going to say 25.52. You know, it's a typo, maybe. Who knows? I'm not going to go back and check my math. But we're just going to say 26.52 here. That's the number that we're going to use. And we'll do this both ways. So if it was truly 1 gram per mil, then we will compare our results to that 26.52. We know that 26.52, though, is incorrect because it's not exactly 1 mil per gram, 1 gram per mil, but we're going to pretend like it is in the first round. And then we're going to compare it to the 25.52, which is going to be probably slightly corrected for the actual density value of water. And that is going to give us a more corrected number that we can go by as far as the volume delivery. So A is going to say what's the average mass, and B says what's the standard deviation, and C says, well, okay, if this is what the burette says that it can do, is it actually doing that? So it looks like we need average and standard deviation. I'm going to go through the Excel piece just as a quick review. I think it's always good for you to hear this kind of stuff. So here's the data, blah, 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 blah. There's the 6 data points, and I need to calculate the average first. So I'm going to key AVERAGE, right? And I'm going to go here and put that number there. So that way I know what that number is supposed to represent. So I'm going to start off with equal. Oh, okay. Excel wakes up and it says, what do you want me to do? So he's so happy. Excel gets very excited when Excel does calculations. So I'm going to type in the word average. And when I type in the word average, I'm going to highlight the data. There we go. And then when I highlight all the data, I'm going to hit enter. Bing, bing. And then it gives me that really difficult calculation of average. So 25.4095. Oh, well, thank you, Excel, for doing all the math work for me. You are a lifesaver. I love you. All right, so STDEV, not STIDEV, but STD. Oh, gosh, I hope not. All right, so there's STDEV, so standard deviation, so that way I know what that number represents. And I'm going to hit equal. Ding, ding, ding. And then Excel is like, yay, I get to do more math. Oh, send me to the math competition. So I'm going to hit equal, and I'm going to type in STDEV. And when I do that, I open the parentheses up, and then I'm going to highlight the data just like I did before. There we go. And then when I do that, I'm going to hit enter. Ta-da! So it's gave me the STDEV value, or standard deviation. All right, so I like for my decimal numbers to match. So all of these have been recorded with 4 digits after the decimal. My average has 4 digits after the decimal. And then I also like for my standard deviation to have 4 digits after the decimal. So in order to shorten that a little bit, because it looks like I've got an extra digit here, I'm going to go up into the toolbar, and when I do that, there is an alignment, right there it is. And if I see that arrow that points left or that arrow that points right, that is for tabs, and that is for indentions. So that is not really what I'm after. What I'm after is right there beside of it. It's an arrow that points left and an arrow that points right, and there's numbers that are assigned with it. So I need the number to go shorter, and I'm going to hit the arrow that points to my right hand, and that will shave off that last digit, and it will round that number the proper way. So that is matching now the number of digits after the decimal point, and it just looks a little bit better. It looks a little bit cleaner on the spreadsheet because of that. All right, so now what's going to happen is that the problem says the burette has a specification sheet, and it states that it should be delivering a volume of water within 0.02 mils. All right, so I've calculated the average. I've calculated the standard deviation. I'm going to say, well, what if our density was exactly 1 milliliter? right? What if that was the case? Okay, that's not a big deal. We're going to say the density's 1. I was supposed to deliver 26.52 milliliters of water. So at 26.52 milliliters is going to be 26.52 grams. If that's the way that that works out, that is the volume that I should be getting as I deliver in the burette. So if I look at the average value here, 25.4095, folks, that definitely is not plus or minus 0.02 from that value. There's no way that that's even close. So I'm going to put on here, it's not going to work. If I think that that is 1 gram per meal, then I should be getting 26.52 grams when I deliver this volume. And I don't get 26.52, I get 25.4095, which is definitely not plus or minus 0.02 milliliters of what I should be getting, or I guess grams of what I should be getting, right? So that's definitely not going to be off. It's not going to be close. That's going to be way off, and it's not going to work for me. All right, well, what if I do correct for the density of water at that particular temperature, and it says 25.52 is really what I'm after? All right, so 25.52 maybe is the target. So I'm just going to go in and I'm going to calculate the difference here. So 25.52, and then I'm going to subtract that from 25.4095. When I do that, I get a 0.11 difference. And if I go and take a look at the specification sheet, then that 0.1105 difference, folks, that is not going to be appropriate. I need something even tighter and even closer. So because of that, neither one of these values will actually pass. And there's either something wrong with the person's technique, or there's something wrong with a burette, or there's something wrong with her sample. But something's going on that's not really quite lining up as the expected values go. So in part A of this lab procedure, what you're going to see is taking that idea, and we are going to ask you to deliver a certain amount of water. And when you do that, you're going to be writing down grams, and you're going to report those grams to me or to the lab instructor. And then we're going to key those values into the Excel spreadsheet, and we're going to see if you did a good job or not. Our Excel spreadsheet is going to trigger, yep, actually, great job, greens and blues all over the place, good for you, go on to the next part. Or it's going to say, sorry, you don't do very good at burettes, you need more practice. And then we're going to go to you and we're going to say, okay, let's see what you're doing, let's see what your procedure's like, where are you messing up, because we need to figure out where these problems are. All right, so let's just quickly take a look at the procedure here. Part 1, using a burette to deliver 5 milliliters of water. So what will happen is that I'll take a burette, and that burette is going to be loaded up with water. Please overfill it. I'll explain why in just a second, but you're going to deliver 5 milliliters. So you're going to start up here at 0, and then you're going to open the stopcock up, and then you're going to go down to 5, and you give me the mass of those 5 milliliters that you have delivered. You can start all the way from the beginning again. It's a waste of time. I don't know why you would do that. Or you can just start right back off where you left off. So if you went down to 5, then no one says you can't in the next step go down to 10, because you'll have to do it more than once. So 5 to 10 is 5 milliliters. So I can drain it down to the 10 mil mark at that point, and then I'll get an additional weight. And then why fill it up to the 0 mark again? I don't need to. I can just pick back up again where I left off. So if I'm starting at 10 in my next round, then I can go to 15 in the next round. And then in the next one, I can go to 20. And the next one, I can go to 25 if that's what's needed. No one says that you've got to fill these burettes full every single time that we use them. So that is the idea, and that's the intention here with the procedure. I will say that when you get a burette, number 1, these things have been used by someone else, and number 2, they might not have a stopcock. So what's going to happen is that you might have to assemble the stopcock first, and if you do that, great, that's good practice. And then what will happen is that we are using water in this part. So I would like for you to add a little bit of water in here, and I would like for you to rinse the burette with that water. I don't know what's been in there. I don't know if that thing's nasty. That person that could be using it was nasty. Maybe they didn't clean it out. Who knows? Maybe they ate french fries and they got grease and nasty stuff and sludge all over it. I mean, that's something that I just don't know, and I don't trust anybody. And I think the moral of the story, you cannot trust anybody in the lab. And that probably includes me. All right, so I'm going to add water to the burette, and I'm going to take it, and I'm not full, but I'm going to swish it and swash it around, and then I'm going to make sure that I get all the nice goods insides kind of cleaned as much as possible, rinsed at least, and then I'm going to dump out that water. And I do it a second time, and I do it a third time. In the second time and the third time, what normally happens is that I will open up the stopcock, and I will allow that liquid to drain through the stopcock as well, because the stopcock could actually be dirty, and the tip of the burette can actually be dirty as well. That needs a good rinsing. So I want to make sure that I come in contact with every part of the burette that my sample will come in contact with, or my titrant will come in contact with, so that way I know all of the crud or the contamination is now gone, because I've rinsed it a few times and I've made sure of that. So that's going to be the first thing that you got to do. Number 1 says tare the balance, and it will read 0. Place a weighing bottle or a small beaker. I would encourage you to probably use like a 250 ml beaker to a 150 ml beaker. Somewhere in that realm is probably, I think, the best for all of these procedures. So with that said, that is going to go into the balance. You're going to zero it out. Next up, it says fill the burette with water. And we're going to go over the 0 mark in the beginning. The reason that I go over the 0 mark is because, and let's say that 0's here and this is the top of the burette, is because there could be a little air plug that's down here at the very bottom of the burette. And I do not need that air plug there. That air plug or bubble is going to take up space and take up volume, and it messes with my delivery. So if there is a air bubble that is in the tips of these burettes, you need them out. And one of the tricks here is to overfill the burette, open the stopcock up, so that way if there is an air bubble, when you open the stopcock up and drain it, you're going to drain it out kind of fast, and then that pressure will hopefully just kind of push that air bubble on out of that tip. Please look at your air bubbles. If those air bubbles are there, you are not going to get correct data here. It's going to be off, and that's something that we need to kind of pay attention to. So you're going to drain it down to the 0 milliliter mark. Number 3 says place a weighing bottle in the burette, open the stopcock, deliver 5 mils, and then take that container plus water back over to a balance, re-tare it, and put that combination on top of the balance and record what that mass is going to be, or what it is. All right. And then we're going to repeat it over and over and over and over. So that's how this process is going to work. Next up is 10.6 mils. We do the same thing there. I would encourage you to go ahead and fill that burette up at this moment, all the way again, full, drain it down to 0. Then you're going to tare out a balance and then put a container on it and record that mass. And then you're going to take that container, deliver 10.6 mils. Walk that combination back over to a tared balance and record the total mass of those things. And then repeat the process over and over and over. And then finally, 12.85, you're going to do the same thing here. Re-tare the balance, new container, refill the burette, and go to town, just like you did on the 10.6 and the 5. So all of that data is going to go into the data sheet. This is what the data sheet's going to look like. Mass of the empty container up on top. What was the mass after your first 5 mil addition? And then what is the difference for the first addition? Next up is the mass of the container after the second 5 milliliters was added. And then now we're going to subtract for the second addition. So what that means is that I'm going to subtract this total from this total up here. And that will give me the difference, and that will represent the 5 milliliters new that I have delivered at that moment. Then we're going to repeat that for the 3rd, the 4th, and the 5th. All right, so once you do that, let me see your numbers. You don't need to do the subtractions. My spreadsheet will do the subtractions for you, so that way we can quickly just double check your data makes sense. And then at the end, of course, there's going to be a spreadsheet that you will key in this information to. So that's going to be part 1 of the lab. And part 1 is just getting used to a burette. We don't, if you're a new face to 115, we don't want you to feel left out of the pack. So this will be your first time maybe using a real burette, especially if you did those silly little take-home science kits at the house. But it's a real burette, and you'll be using it for real in our lab. And I think that it will be a little more truer to life than some of those little syringes and droppers that you have used in kits if you've taken an online science course. All right, so another video is going to happen, and it's going to focus on part 2 of this day, and part 2 will be all about a titration that we need to tackle. So I will see you again before the lab in a new video. Yay! Woohoo! I know you can't wait.